let's say that we wanted to get an estimate for how long the flight from Sydney to Singapore is. If we were doing something like that, what we might do is collect data. So let's say we collect data on 16 trips that have been made. And let's say from those 16, once we summarize the data, we get that there's an average of 8 hours, let's say 8.4 hours, with a standard deviation of 0.2 hours, and we know that our sample size n is 16. In this case, our single best estimate for how long it takes to get from Sydney to Singapore is just going to be our sample mean. So that's going to be 8.4 hours, and we call that our point estimate. So the point estimate is 8.4 hours. But sometimes we want a little bit more than that. Sometimes we want to know what a reasonable upper and lower bound might be. If you imagine that this circle represents the population, so this is every Sydney to Singapore flight. Obviously, we don't want to get information on every single one. It's going to take too long, too much resources. So what we do instead is just take a sample that we feel is representative. So for us, that's our 16. And from this group of 16, we got a sample mean of 8.4. What we'd like to do with this sample is make inferences about the whole population without having to do any extra work. We don't want to take more samples. We just want to use this sample to try and make conclusions about what would happen if we took other samples of size 16. And that's kind of what a confidence interval does. It tells us what we think the lower bound will be and what the upper bound will be, and what we feel most of these means, most of these samples, where we feel their means will fall if we extended this out. So let's have a look at this example. What we're going to be doing is working out a confidence interval for the population mean. So this is going to be a confidence interval for mu. So the population mean we represent with the symbol mu. And the formula for that is x bar plus or minus some critical value. In this case, we're talking about a sample, and we don't have the population standard deviation, so we're going to be talking about critical value for t, and that is multiplied by the standard deviation over the square root of n. And we can have different levels of confidence. We could have a 90% confidence, where we feel 90% of the scores fall within that interval. We could have 95%, where we feel 95% fall within that interval, and 99%, they're probably the most common. For this example, let's say we're doing a 99% confidence interval for mu. And in order to kind of get that critical value, we have to know what T critical is. It consists of two things. It consists of the confidence level and it consists of the degrees of freedom. So we'll get into both of those. Degrees of freedom for a one sample test is just going to be n minus 1. And your confidence level, let's just work this out, that'll be 16 minus 1, so that'll be 15. Your confidence level is inversely proportional to your significance level, which is alpha, which is represented by this little fish looking symbol. So if your confidence level was 90%, your significance level would be 10%, 95% would be 5%, and 99% would be 1%. And we're trying to work out where the middle 99% of scores lie. So if this is our normal distribution, we're trying to work out what is the upper and lower bound that result in this area here being 99%. This whole graph is 100%, so each of these two tails will be 0.5 of a percent. So this will be 0.5 of a percent. This will be 0.5 of a percent. And that's often why we see the notation, such as I've written here, alpha on 2. We're dividing that significance level on 2 because it's two-tailed. We're trying to see what the middle proportion will be between those two limits, upper and lower limit. So for this one, it'll be T 15 for our degrees of freedom, and then 0.005. So that is just 0.5% as a decimal, 0.05. And now that we have that, we can look that up in the tables. So we just look up in the tables and we can see that we've got one tail being 0.005, two tails being 0.01, and we go down to 15 and we get 2.947. So we've got X bar, which was our sample mean, 8.4, plus or minus 2.947, multiplied by the standard deviation, so multiplied by 0.2, divided by the square root of 16. This bit on the right of the plus or minus, that's known as our margin of error. And what we want to do is work that out first. So we're going to do 0.2 divided by the square root of 16. So 0.2 divided by 4. And then we're going to times that by 2.947. And that gives us 0.14735. So we've got 8.4 plus minus 0.14735. Let's just call that 0.147. And now what we can do is plus and minus that. So by convention, we're going to minus it first. So we're going to do 8.4 minus 0.147. And we get 8.253. And then as our upper bound, we're just going to do 8.4 plus 0.147. And we get 8.547. So that is the confidence interval worked out. Let's think about what we've actually done here. Worked out that the point estimate was 8.4 hours. That's our single best guess. And we're saying that if we took, let's say, 100 flights, 99% of our samples would have an estimated population mean somewhere between 8.253 hours and 8.547 hours. So it just gives us an upper and lower bound of what we feel might be reasonable for our estimate. We can see that with our confidence interval, our point estimate falls exactly halfway in this case. So let's say we had that confidence interval. Let's say we had 8.253 to 8.547. Let's say we just had that information and we wanted to work out what the point estimate was. All we do is add those two bounds together and divide by 2. So we do 8.253 plus 8.547 in brackets because we want to do the addition first. And then we divide that by 2. Let's just work that out. 8.253 plus 8.547 divided by 2, and as expected we get exactly 8.4. So that's how we can work out the point estimate given the interval estimate, just adding them together and dividing it by 2. Sometimes we're also interested in using confidence intervals to work out how big a sample we need. So let's do that on a new page. So you've seen that we've got confidence intervals which express an upper and lower limit for a point estimate. So what we would expect the point estimate to lie between, realistically or theoretically, if we took many samples, and we'd say maybe we expect 99% of the time we expect the mean to be somewhere between 8.253 and 8.547.